So today I'll be talking to you about visualizations that can help you build better predictive models. So a quick note on me, I'm a data visualization engineer at DataRobot. We have a booth downstairs. Many of you have probably checked it out before, but if you haven't, go check us out. We're essentially a machine learning platform for data scientists of all stripes. And as a data visualization engineer there, I specialize in making visualizations that look really cool, like that, instead of like this, the dreaded matplotlib. And yeah, today I'm going to be talking to you about how visualizations can help with your predictive modeling. So the so-called old way of doing things is that we'll typically do a lot of feature engineering. We'll build models, we'll validate those models, and if those models are any good at all, we'll use them to make predictions. But what we do at DataRobot, and what I'll really emphasize here, is starting the modeling process as early as possible, and then using model interpretation visualizations to help with your feature engineering so that this so-called new paradigm of doing things, becomes more of this cyclic, iterative process. And I'm going to use a data set that I found on Kaggle to demonstrate some of these visualizations. So we're going to go through like an example prediction problem. And as a quick disclaimer, can you guys hear me okay? This thing keeps wobbling. As a quick disclaimer, I did give a very similar talk at the last ODSC in Boston, but there's probably a little intersection there. But if you have seen it before, I guess you can leave and I won't be offended. Unless you're my coworkers, then I will be really offended if you leave. So the prediction problem we're going to be looking at today is predicting election meme popularity. That's really exciting, right? You get to see memes. Yeah, so more specifically, predicting the number of likes a meme related to this latest round of US presidential elections is going to receive once it's out in the wild. Yeah, I thought this was a very topical data set since the election is right around the corner. Memes are basically taking over the earth. There's literally a subreddit called the meme economy where you can invest in memes. Not something I've done yet. But I am a millennial, so I really like memes. This is the most millennial talk you'll hear all weekend. What is a meme? I think you guys all know what memes are, but this is an intergenerational audience, so I didn't want to I wanted to make sure everyone knew what a meme was. The traditional definition of a meme is that it's an idea, behavior, or style that spreads from person to person within a culture, kind of like a virus. And the typical way that it manifests on the internet is as this reusable picture that can be captioned in culturally relevant ways. So these are two examples of data science memes predicated on certain cultural knowledge that we all share. So one example of a cultural context that we're all in right now is ODSC itself. So ODSC has its own memes. So if you guys were at the keynote, you probably heard my CEO, Jeremy, talk about how one of our colleagues, Ben, looks like Tom Cruise from certain angles. And yeah, Ben, could you stand up again? No, you have to actually stand up. I'm not our CEO, so I don't have the power to make him stand up that much. Ben, this is exposure therapy. This is okay. This is how lives are ruined, by the way, creating someone into a meme. But it's also how memes are formed. They're formed. Jeremy made a joke. I'm turning it into an image and perpetuating it, and therefore turning it into a cultural trope and a meme. So feel free to circulate that. Okay, so back to data science. So let's take a quick look at the data that we have. I looked at a subselection of 14,000 Donald Trump and Hillary Clinton memes. The data that we were provided with was number of likes the meme got. Unfortunately, this is not normalized by the number of views that the meme got, which is probably what you would want to do if you were a good data scientist and wanted to capture an actual signal of popularity. Author who posted the meme, the network the meme came from, whether it was Facebook, Instagram, Twitter, whatever, the original link to the post, when the meme was posted, and finally the most important variable, the extracted meme text. So Kaggle used Yeah, this data set is from Kaggle, and Kaggle used like character recognition to extract the text from the meme. So that's mostly what we'll be focusing on right now. This is like by no means a comprehensive feature engineering step. You'd probably want to go and collect all the actual memes and do like some cool image recognition stuff. You could do like image hashing, deriving all sorts of image features, which is like this like deep dark hole I went down for a bit, but wasn't good for the purposes of this talk, which is mostly about visualizations. But I did, since it is text-based data, I did run some topic models over the meme text to derive some topics from those memes. I'll get into that a bit later. Okay, so let's look at a first set of visualizations, going through some data exploration. So let's look at the distribution of likes across our data. We can see that this kind of skewed long-tailed distribution corresponds to something that we might expect. So most memes are not that popular. Few memes actually do go viral, but there's still like a big chunk that do go viral that are represented in the last bin there. And it's also really important to look at the distribution of likes across variables in our data. So for example, looking at likes across time, and we can see that there's a lot of volatility there. So for example, there's that big spike in the middle, and then it goes down like a commensurate amount, and there's just like a lot of volatility, and then there's like that slump, and it's like, this is not actually a plot that I expected when I was looking at this. I thought that average meme like would actually increase the closer that we got to the election, because presumably those memes would become more relevant the closer we approach this day of reckoning. But that doesn't seem to be the case. So what seems to be the case, if it's not like meme fatigue or whatever? Well, one way that we can answer this question is to give ourselves a little bit more context. So underlaying this plot with a histogram of the variable distribution immediately shows us that a lot of the volatility in the data might just be attributable to noise. So we can see that there's just like not a lot of data where there's a lot of volatility. And maybe the statistically significant trend that merits further consideration is the one that's like where there's a lot of data. So we don't actually want to use this variable in our analysis when we're building models, because having just like the date as a variable won't be very useful at predict time. But let's look at some variables that might be important, the topics that we derived using our topic models. So I don't really know how fluent everyone is in like topic modeling, but probably a lot of you are as like data scientists. But just a quick overview of a topic model. It's basically just a statistical model that finds topics from a collection of documents. And then you can use those models to assign topics to a document, or in this case, a meme. So this is a meme that was in the data set. So on the surface, this meme is about Melania Trump, it's about Michelle Obama, it's about term papers being due at a certain time. It's about like college anxiety that we all know and love. And at a more semantically relevant level, it's about Melania Trump plagiarizing Michelle Obama's speech, if you guys all remember that. So with like our human intelligence, we know that those are like topics that the meme is about. And hopefully a machine would be able to figure that out too. For the purposes of this analysis, I built two topic models. One trained on a held out section of the Trump meme data, so those meme text captions, and a second one trained on the a held out section of the Hillary meme data, so that text data. And this is a subselection of the topics that those topic models found. And I'm putting them all up here because I thought they were interestingly cohesive. Since like memes are from the internet and the internet is full of like trash, I didn't expect them to like be this cohesive. But you can see like that first one there, topic one, in the Donald Trump memes is like about his latest transgressions, talking about women. And then there's some about like, there's some that include the words MSNBC, CNN, so that's probably about Hillary's like appearances during debates or whatever. And then there are 2 other Hillary memes that encompass, that contain the word WikiLeaks, arrest, emails, campaign deleted. So that's, obviously about her issues. But we're going to specifically look at one, topic 9. Yeah, topic 9, that sounds like so dystopian, like Area 51, topic 9. Okay, but a topic can be represented by a set of words and a distribution of words. So these are the top 10 words that describe topic 9 and their corresponding probabilities. So they contain Trump, like, white, just, frog, other words. I call this one the alt-right meme, or topic, the alt-right topic. What? I heard someone say something, but. So I can't really show you the memes that went into describing this topic or building this topic because they're honestly probably too offensive and politically fraught to put up on here. But let's look at another one. This is Donald Trump. Sometimes we put up walls, not to keep people out, but to see who cares enough to knock them down. It's so sad. So if we take a gander at this with our human eyes, we can tell that it's talking about Trump, it's talking about walls. So let's see what our topic models think. Here is a donut chart, which is very sly of me to slide in a pie chart or something related to a pie chart into a data science conference because data visualization people hate pie charts, and this is super controversial. But the machines found a certain amount of salient topics relating to Hillary, and then a certain amount of topics relating to Trump. So we'll look at these, and I thought this one in particular was really interesting, topic 4. It can be described by these following words. Donald Trump, wall, Hillary, America, Will says great, make. So these are all words that we should be familiar with at this point. They're words that basically describe Trump's campaign or his political platform. He wants to build a wall. He wants to restore America to its former greatness, make America great again. And I think those words are represented here. So it's interesting that that meme that we just saw can be represented by this one topic that kind of represents his political platform. So keeping that in mind, let's look at another visualization, a predicted versus actual chart. So let's say that we've built some models, we've trained them, we're validating them on a held out set of our data, and we're going to see how that model performs across a certain variable, across a certain feature that went into building our model. So this is the distribution of topic 4, so the topic that represents Trump's political platform. And as we can see, exhibits sort of this vague U-shaped behavior. And the way to interpret this is that it looks like memes that are not that are almost not at all about Trump's political platform, and memes that are almost entirely about his political platform. You would expect those to get a higher number of likes, and the other ones don't. So then we can plot how our predictions are doing across this variable. And the question we want to be asking here is, how well does the model fit the data? And the answer to that question here is that it seems to fit it pretty well up until we get to a certain point where it subsequently deviates catastrophically from the response. But again, if we underlay it with the histogram of the actual variable, we can see that that volatility is probably just attributable to noise. So this might seem really straightforward, but one of the big points of this presentation is about storytelling and communication. And so this kind of thing becomes really important when you're trying to convey your results to non-experts. So let's say that you're trying to sell these models to Bernie Sanders. Bernie Sanders' political machine, Bernie Sanders' dank meme stash, only wants to release memes that they're sure are going to get a certain number of, or a high amount of likes. So is Bernie going to buy your model because the Gini norm is a really nice value? Or is he going to buy it because a visual check showed that the model was performing well across variables Bernie is familiar with? So I think we all know the answer to this, right? The first is totally divorced from his reality, but the second shows him that the model has actually learned a trend, or that it hasn't learned a trend. And if it's performing poorly, the underlaid histogram gives him context and can help him explain why it hasn't been performing well in those areas. And that, in turn, helps instill trust in the user. Because at the end of the day, a user is going to be using the model, and you want that user to be able to trust the model. And at the end of the day, we want high-quality memes. So just a quick recap. Yeah, histograms are useful for data exploration, but they can also be used in less obvious contexts, such as underlaid with your target plot or your predicted versus actual plot. And again, they help instill trust in the user, so they're very good for communication. Okay, so we just saw how we can see how a model performs across a given variable, but how do we assess just overall model performance? What kind of visualization can help us just give like a quick glance and let us know how it's doing? The lift chart measures overall model performance. So I'm going to show you a lift chart for one of our highest performing models, which is essentially just like an ensemble method that combines predictions from a variety of regression models like SVM regressor, random forest regressor, some others. The way that you plot a lift chart is that you sort your predictions from lowest to highest, and then you sort them into you bin them into percentiles. So for example, that last point in the 10th percentile basically just shows you the average prediction in the top 10% of your predictions. And then you can plot the corresponding actual values, and you have your lift chart. So one of the first things that you want to look for here is whether or not the two lines trend closely together. And here you can see that they kind of do. You can see that we're at least doing way better than average, than random. Or if we were just like predicting the mean, we'd just have like a pretty straight line, and then our actual line would be like fluctuating erratically. A second thing you want to look out for is if your actual line is monotonically increasing. So since our predictions are sorted from lowest to highest, you want a monotonically increasing actual line. So that gives you a sense of like how precisely your model is making predictions. So for example, if your model was just like capturing a general trend, but then it was missing the mark in each bin, then you would see it like kind of fluctuate more, which would be violating monotonicity. And if we were to zoom in on this at a higher resolution and say look at like 100 bins, then we'd probably see like more erratic behavior. And then finally, a third thing that you want to look out for is lift, which is basically just the steepness of the line. And in that case, lift tells you how well your model is doing at differentiating between low and high values. Or in the case of like binary classification, how well it's doing at distinguishing between two classes. So here we can see that we don't actually have a lot of lift, which tells us that our classifier is a bit less confident at distinguishing between high and low values. So like in the most extreme case, a classifier that's not confident at all might be just predicting pretty much the same value, and you'd get a straight line. And if it's bad and not confident, then you would also see a very erratic actual line. But if it's very confident, then you'll still see that line that has a lot of lift, but you'll still see this like erratically fluctuating actual line. But going back to our original lift chart. So one thing that concerns me about this lift chart is that I can see how well predictions are doing on average, but that doesn't really tell me like how reliable those predictions are. So I want to be able to kind of get like, well, in order to be able to get an estimate of the expected error at each level of the response, I can plot quantiles around our response. So I want to plot the median, the top and bottom 25%, and then the top and bottom 10%. And this confirms our worst fears that the model is actually not doing so well, like in that 10th percentile, because we get like a ton of spread around our predicted value. So it looks like what we were saying before, it's not that confident at making predictions. It tends to make low predictions, and then the actual values therefore get concentrated in the last bin, and that's why we see so much spread there. So if we zoom in a little here, we can see that, for example, in this percentile, when our regressor predicts around 4,000 likes, the actual response is going to be between 1,000 and 5,000 likes. So this is useful, for example, if Bernie Sanders only wants to release a meme where he's at least 90% confident that the meme will get at least 1,000 likes. And that's sort of like a contrived example, but you can imagine a lot of other examples in like insurance pricing or something where they'd want to make sure that they adjust their price with like a certain amount of confidence. Okay, so quick recap on the lift chart. You want to be looking for 3 things when you look at a lift chart. You want to look for fit between actual and predicted, which kind of gives you like a visual estimate of how accurate the model is being. You want to look for a monotonically increasing actual line, which gives you a visual estimate of precision. And finally, you want to look for lift, how steep the line is, which tells you how well the model is doing at differentiating between low and high values. And you can add quantiles as a sort of visual estimate for confidence intervals around your prediction. Okay. So yeah, lift charts give you an assessment of overall model performance, but it doesn't tell you exactly what's going on inside the model. We really want to be seeing how individual predictors in our data set contribute to the outcome. And we can use the partial dependence for that. Partial dependence plots the marginal effect of a predictor on the prediction. Yeah, when I first saw that definition, I was like, what does that mean? But we'll go through an example. So let's say we want to see what kind of effect network has on the outcome. So network is where the meme originated, whether it came from Facebook or Twitter, Instagram, Imager, whatever. So in order to figure that out, we have to calculate the partial dependence for each value that network can take on. So just to go through a quick example, we're going to calculate the partial dependence for when network is equal to Instagram. So all that we do is we take our validation data, we fix every single row of the network column to Instagram, and then we make a whole new set of predictions on that, average over them, and that gives us our partial dependence value for when network is equal to Instagram. And then we can do this for every single value that network takes on, which are these. So let's take a quick look at, whoops, I plotted 2 things too quickly. So this is our predicted versus actual chart from before. So we can see that in the raw data, there does seem to be a trend. Instagram seems to get like a lot of likes. Facebook, Imager, and Twitter get fewer likes. Imager gets like literally like negative likes. And I can confirm that looking through the data, a lot of the Imager memes were like literally so horrible. They were like physically painful to look at and not funny at all. So the problem with our predicted versus actual chart is that it doesn't take, even though it tells us that the model is performing well across this variable, it doesn't take into account potential correlations with the variable. So if network is correlated with some other kind of variable, then we could be seeing the effect of that correlated variable instead of the effect of network. But we can confirm with our partial dependence plot that the network variable does seem to, in fact, be having an effect on the outcome, though it doesn't seem to capture the entire effect. So yeah, just a quick recap. Partial dependence shows you the relationship between a predictor and the prediction by calculating the marginal effect of a predictor by fixing it first for each of its values. And unlike the predicted versus actual chart, it doesn't take into account correlation with other variables. Okay. So now let's say that you have a whole lot of variables, like let's say you have like 1,000 or 5,000 variables. So you're not going to go and look through every single partial dependence plot for those, for some insight from those. You want to try to get like a prioritization of features that are worth investigating. And that's what variable importance is for. Variable importance is basically a collection of methods that helps you rank order variables by the size of their impact on the target. And so at DataRobot, for example, we have several ways of computing this that are both feature type and model agnostic, which means that you can actually rank order variables that have different types, like categorical variables, numeric, text, whatever, and you can compare those across models. So this is really important because, as I mentioned earlier on in the talk, you want to be able to use visualizations to help drive future cycles of feature engineering. And variable importance can help you with that because since it gives you like this list of variables that are important to look at, you can go ahead and build new models using that. So yeah, let's look at a quick example. I'm going to look at a specific method called permutation importance on our caption variable. So as you recall, that's just the text that was extracted from the meme. So all we do is we shuffle the caption column in our validation data, and then we make a whole new set of predictions on that. And then our importance score is really just the difference between the score of the predictions on the full data set and the score of the predictions on the matrix with the permuted column. So score being just like whatever metric you use to optimize the model. And then in order to rank order the variables by importance, we take our most important variable, we normalize it to 1, and then we rank all the other ones as a function of this most important variable. So immediately we can see that there are a few ones, and this is like actually a cutoff chart. So there are a bunch of variables that we use in our initial analysis that have like near 0 importance. So immediately we can see that maybe we don't even need to use those variables anymore in a future cycle of modeling. And this is really important if like you're consuming a lot of time and resources gathering data for one of the variables. Like let's say you have like sensor data or something, and one of your sensors take a lot of, it is very expensive to maintain. If you see that this sensor doesn't actually have importance across a variety of models, then you can just get rid of it, maybe, and save a lot of money. And again, this is also really, this is like one of the best visualizations that you can use when communicating your results to a non-expert, because they can immediately use their domain expertise to see that this result makes sense and that there's not like anything crazy going on because these are all variables that they're familiar with. And in terms of our personal analysis, we can see that the most important variable is author. The second most important variable is network. So it looks like, if you're a certain author that presumably already has a lot of memes that people like, and you produce more memes, then they're going to like that even more. Same with the network; those two are probably correlated. Some of the topics have a certain amount of importance, and then some of our derived features, like hour of day the meme was posted, has an impact. That's kind of interesting. Yeah, so just a quick recap on variable importance. I showed you specifically the permutation importance method, but then there are other ones. Scikit-learn has some other types of importances that you can look at. Gives you insight into your prediction problems. Like I said before, it helps you prioritize features that merit further investigation so that you can go ahead and continue future rounds of feature engineering. Also helps you reduce data collection costs. You can compare variables across models, so it's also kind of like a model comparison technique. And finally, it helps you communicate results. That was the last chart. So some key takeaways. How to create a successful meme, something that plagues us millennials. Already have successful memes, as we saw from our variable importance chart. I say this kind of in jest, but it is true that with this kind of like network phenomenon, people who already, have a lot of followers and the generate new memes are like obviously going to get more likes because the rich get richer. So here's just like a quick recap of the charts I went over. Histograms help provide context even throughout your modeling process. Lift charts are good for a quick visual assessment of overall model performance. Your partial dependence helps you assess if predictors have an effect on the outcome. Your predicted versus actual shows how your model is performing across certain variables, and it does take into account correlations potentially with other variables. Variable importances provide a prioritization of features. And again, start modeling early so that you can make use of those visualizations in future rounds of modeling. And finally, use interactive visualizations because they're really cool. They look cool, they're fun, they're engaging. They made this presentation take an unreasonable amount of time to make as well. And thank you.